So for this next short lesson, we're going to talk about the phases of matter. And basically what we're talking about here, there are three phases of matter that we're going to focus on in chemistry. The first one, of course, is solid. The second one is a liquid. And the third one is a gas. Technically speaking, there are four phases of matter. And the fourth phase of matter is plasma. If you ever want to study about plasma, you have to actually be a physics major and actually major in what is called plasma physics. Most of the time, chemists do not deal with plasma. Now the biggest difference is, of course, that you need to make sure you understand structurally is what happens at the microscopic level for all these three phases. And you need to have these pictures or models in your head when dealing with these three phases. In a solid phase, you need to know that in a solid phase that the structure is very organized. There is a crystalline structure in this phase of solid for the solid phase. In liquids, on the other hand, sorry, there's something going on over here. Escape that. Escape. In liquids, on the other hand, what you will notice is that the structure is not organized. The molecules in the liquid phase move all about each other. They're jiggling, they're moving around each other. That's why they can take the shape of the container. Last but not least, in gases, the gases, of course, you can even see are even less structure. They're even further apart from each other. And when we talk about spacing between the three phases, in general, solids are very tight and compact. Liquids have a lot of space between them, and gases have a lot of space between them. So much so that there's no interparticle interactions other than when they collide with each other. And so you need to make sure you have that picture in your head. So what makes each phase the same for gases? Well, as long as we're assuming a pure substance, they will all have, the only thing they'll have in common is the fact that they either have the same atoms in there or the same molecules. So when I talk about pure substance of water container, like in my water container in here, then what we're talking about is it only have H2O molecules in there by itself. Nothing else, just H2O. And if I'm talking about gold, assuming 24 karat gold, which this is not, then in this solid it would only have gold. And if I melted it, it'd still be gold. And if I change it to a gas, it'd still be gold. So between all three phases, they'd only have gold. For water, it would be ice, would be all water molecules. As a liquid, it'd be water. And gas, steam, would also be water. Other than that, there's not much difference. I mean, nothing much the same. But there's a big difference between them in the phases. And the speed at which the particles are moving are very different. Solids barely move at all, they're vibrating in place. Liquids are tumbling around each other. And gases are really moving and shooting across the space that they are flying in, constantly colliding with different things and just moving at very rapid pace. So the speed at which they move is much greater for gases and much slower for solids. The distance between each of the particles are also different. And as you go from solid to liquid to gas, the distance between the particles become greater and greater. Unfortunately, as a side note, water is one of the few exceptions. That's why water as a solid can actually float in water liquid. Otherwise, it would be the other way around. And then last but not least, because of that, they have different physical properties. Their temperatures would be different. Gases are typically at a higher temperature than their solid counterparts. The densities would also be different. Typically, gas densities are a lot smaller than the densities of solids. And the structure, of course, gases have no structure, solids have structure. So all these things are different within the three phases, and you need to have that picture in your head on how they are different. Now, because the temperatures are different, I want to introduce the topic of temperature and what it means. By definition in chemistry, it measures the average kinetic energy of the atoms or molecules. And so kinetic energy, by definition, in physics, has a formula of 1/2 mv squared, and we'll revisit this formula later. But it's dependent upon the mass and dependent upon the velocity at which it moves, or the speed at which it moves, squared. So the faster it moves, the more kinetic energy it has. And typically we always say that absolute zero, or 0 Kelvin, is the point at which all molecular motion ceases. So anytime we talk about temperature, if we ever get to what is called absolute zero, which is roughly negative 273 degrees Celsius, then this is the temperature which all molecules and atoms become a solid, basically. because they are no longer moving, so they're going to all have some kind of structure. And when we deal with these things, one of the things that you need to make sure you understand a picture of is that when we say something has a temperature of 50 degrees Celsius versus 100 degrees Celsius, you need to understand that not all the particles in there have the same kinetic energy. And so when I look at something that has, when I look at something that has 100 Kelvin, what you need to understand is that at 100 Kelvin, so that would be at this point right here, I have molecules in this region right here that have temperatures greater than 100 Kelvin. And likewise, if I'm at 500 Kelvin, I'll have molecules over here greater than 500 Kelvin within that same system. And at 1000 Kelvin, I will likewise also have molecules that have higher temperatures than 1000 Kelvin. This explains to us why water has the ability to evaporate in a liquid state. Just because it's 30 degrees Celsius doesn't mean that there's not any molecules in there that are moving at a high speed. And that allows them to escape and evaporate, even though the temperature of the water may only be 70 degrees Fahrenheit, just like the ocean was during the summer. Doesn't mean it's not going to evaporate, because the sun is hitting it. It has the ability to warm up some of those water molecules, and the few of them that are at that temperature that can evaporate will evaporate. Okay, and so that helps us understand a few things in there. And so in terms of converting, for our class purposes, we just need to know how to convert between Celsius to Kelvin. So to convert between Celsius to Kelvin, it's a simple temperature conversion. All you do is add 273 if you want to change to Kelvin, and likewise you just want to subtract 273, doing a little algebra, if you want to go back to Celsius. So Kelvin to Celsius, you subtract; Celsius to Kelvin, you add 273. And that's a formula you need to make sure you know. So why don't you practice these two problems? I'll pause it right here and I'll give you the answer. So for this first one, according to the formula, temperature Celsius is equal to temperature Kelvin minus, plus 273. Sorry, I'm doing the formula wrong, so it's backwards. Temperature Kelvin is what I want, which is temperature Celsius plus 273. So 100 plus 273, in this case, would be 373. 373 Kelvin. And likewise, going backwards, if I want temperature Celsius this time, I need temperature Kelvin minus 273. And when I do that, I will put 0 Kelvin minus 2, I don't need to put the Kelvin there, minus 273. And so that would be negative 273 degrees Celsius, which is what I said earlier when I talked about absolute zero. So that's quickly how you do temperature conversions. In terms of phase differences, again, when we talk about states of matter, I think I went through this already. Structure for solids. When you talk about liquids, of course, there is less structure. Gases have too much space, and of course, plasmas. And so as you add more heat, you can change the phase from solid to liquid to gas to plasma. That's why the sun is pretty much in the plasma phase. Solid, by definition, has a definite volume and a definite shape. Particles packed in fixed positions. Liquids have definite volume but indefinite shape, particles close together but not in fixed positions. Gases neither definite volume nor definite shape. The particles are at great distances from one another. And then last but not least, the plasma has high temperature. It's ionized phase of matter as is found in the sun. And when we talk about this ionized phase of matter, we're talking about how if this was a helium molecule, like it would be in the sun, or helium atom in the sun, then that helium atom in the plasma phase would have, let's say this green over here would be the helium that has lost an electron, which would be a plus charge or plus 2 charge. And of course these would be my electrons that would be flowing around everywhere in that state. So that's all for the phases of matter. I know that was a little long lesson, I apologize, but I needed to drive home this concept of how these phases are different and how you need to make sure you have a visual as to how they work. Okay, so of course, if I want to cool them down, again, you just have to make sure it goes to the solid structure there, and that's it for now. Okay, thanks.